Hey guys, Schrödinger equation is one of the most important and famous equation of quantum mechanics, and in this video we are going to derive the Schrödinger equation. So without wasting any time, let's get started. So here's the basic wave equation that we use in classical mechanics. From this we are going to derive the Schrödinger equation. So first of all, we have added a term minus iota a sine omega t minus kx to this equation. Now notice that we have added this term only on the right side of the equation, not on the left side. And the interesting thing is that the equation still holds true. But how? This is because that the term we added contains iota, that is an imaginary number. So it will not influence any property of the wave in the real world. So basically we can add any term containing iota and subtract any term containing iota from this equation. Then why we add or subtract this specific term minus iota a sine omega t minus kx? This is because of the Euler's formula. And here theta is equals to omega t minus kx. Now we will take a common in the first equation and we will get a similar expression as that of Euler's formula, and by using Euler's formula in that equation we will get y is equals to a e to the power minus I omega t minus kx. Now I have replaced the y with the Greek letter psi, which is also known as the wave function of our particle. Here it is a function of x and t, as you can see in the powers of e. The wave function contains all the information about our electron or particle which we are studying. Before proceeding further, I would like to change the omega and k of my equation in terms of Planck's constant, which is the most fundamental constant of the quantum mechanics. So from classical physics we know that k is equals to 2 pi by lambda, where k is the wave number of the wave and lambda is its wavelength. Now remember the de Broglie wavelength from your high school physics, which says that lambda is equals to h over p, where p is the momentum of the wave. Now we will substitute the value of lambda from de Broglie wavelength to the above equation and we will get this expression, which is k is equals to 2 pi p by h. Now we will write this equation in terms of reduced Planck's constant and we will get k is equals to p over h bar, where h bar is the reduced Planck constant, which is just equal to h over 2 pi. Now again from classical physics we know that omega is equals to 2 pi over t, and in terms of frequency it is 2 pi nu, where nu is the frequency. Now from Planck's law we know that energy E is equals to h times nu, and we can write nu as E over h. Now we will substitute the value of nu from Planck's law in the above equation and we will get omega is equals to 2 pi E over h. Now we will replace h over 2 pi as the reduced Planck's constant h bar and we will get omega is equals to E over h bar. Now I have both k and omega as a function of the reduced Planck's constant. Now I will put the value of both of them in this equation and I will get an expression like this. Now taking h bar common in the power of e, it will become this. Now we are going to differentiate this equation with respect to time. Since it is a multivariable function, we will use partial differentiation to differentiate this function. First of all, a is a constant, so it will come out of the differentiation, and the differentiation of e to the power something is just e to the power something, so it will remain unchanged. But now we will use chain rule to differentiate that something which is in the power of e. Since we are doing partial differentiation, we will consider everything as constant except t. So the differentiation of this will be minus iota e over h bar. Now notice that the first term in our differentiation is same as psi, so we will replace this term with psi and we will get, now by little rearrangement you can get up to this equation, and by performing rationalization you will get up to this equation. Remember this equation because we will use it further. So I'm going to mark this equation as equation number 1. Now we are going to differentiate our wave function with respect to x, just like we differentiated with respect to t. The same process will again occur. There is a constant, so it will come out of the differentiation. Again, it will e to the power something will remain unchanged. But now we will treat t as a constant and x as a variable. So we will get minus iota p by h bar as the extra term, which is in multiplication with our first term of the differentiation. Now we are going to differentiate again this equation with respect to x. Now all the process is just the same as we did above, but in the last of this equation we will get minus iota p by h bar squared, which when we open square, minus got cancelled and we get iota square p square by h bar. Now writing the first term as psi, we will get psi iota square p square by h bar square. Now by little rearrangement you can get up to this equation. Now this equation will have further use, so I am going to mark this equation as equation number 2. Now we all know that the total energy is just equal to kinetic energy plus potential energy, and we can write kinetic energy as p square over 2m. You know it from classical physics. Now I'm going to multiply both sides of the equation by our wave function psi, and we will get this equation. Now I'm going to replace E psi from equation number 1 with iota h bar del psi over del t, and I'm going to replace p square psi from equation number 2 by minus h bar square del 2 psi by del x square. Now the equation we get here is the Schrödinger equation, but it is valid for only one-dimensional motion. But our world is not one-dimensional, it is three-dimensional. So for making this equation three-dimensional, we have to just replace del 2 psi over del x square by del 2 psi over del x square plus del 2 psi over del y square plus del 2 psi over del z square. This is also known as the Laplacian operator. So if we replace that gigantic term with Laplacian operator, our equation becomes like this, and this is the familiar Schrödinger equation that you have seen. So we have finally derived the Schrödinger equation. See you in the next video. Till then, be curious, stay happy, and Jai Hind.